Hello everyone, I'm Seungjae Lee. Today I'm going to talk about 3D particle or maybe particle scale geometric characterization to better understand the complex macroscopic soil-water interaction problems. So these soil-water or particle-water interaction problems are actually everywhere, ubiquitous, including brewing coffee. So here you see the different geometry of the coffee grounds, such as the particle size. So this different geometry of the coffee grounds is a major factor that determines how the coffee interacts with water as it passes through. So for example, if the grounds are too coarse, the permeability becomes higher, and then that makes the brew time too short. That results in sour flavor or something like that. So likewise, in hydraulic engineering, it is very important to characterize the particle geometry because that determines how the soil or particle interacts with the water. The interaction is severely affected by the particle geometry. Simply because many hydraulic structures are made of particles such as dams and levees. However, despite the significant advances in hydraulic engineering, these hydraulic structures keep failing, not only in old days like 1976, but also present days like 2 months ago. So, hydraulic structure may fail under obvious immediate external stressors such as heavy rainfall, but there are also the time-dependent processes that cause the hydraulic structure fail over extended period of time, such as drain accumulation, the creep, erosion, piping, and fine-grain migration causing clogging, time evolution of soil properties with particle geometry change, such as caused by crushing. On top of this, we face design challenges caused by climate change and higher flooding risk. So nowadays, the dams and levees are constructed worldwide, are getting larger, bigger, taller, and reservoirs are getting deeper these days. That causes higher chances. That increases the chances of particle geometry change, such as the particle crushing. So as the dams are getting bigger, that is increasing the pressure at the bottom of the dam that actually crushes the particle. So at this point, I like to ask myself, is that still okay to use the traditional design criteria method? Because we have a design challenges caused by this climate change and higher flooding risk. And also we have seen hydro structures keep failing. So let us see how we have considered the particle geometry so far. We actually focused on particle size distribution. For example, the filter design is a function of the particle size. So this is a traditional Telchagis or filter design method that requires to compare the size of filter material to the size of the core soil materials. So likewise, the permeability estimation is also a function of particle size. So here you can see a number of equations starting from Hazen. So you can see the permeability is simply a function of the particle size, such as D10 and D50. All right, then I'd like to ask myself again, can you do this better? Because the particle geometry is not simply size, because 3D particle geometry has 4 dimensions. Not only size, but also surface area, A, and volume, V, and also the shape. So I will use a symbol beta, okay, such as angularity. So in the engineering practice, we have qualitatively classified or characterized the particle angularity like rounded, subangular, and angular, right? So, but with thanks to the recent advances of the 3D scanner, so now we can quantitatively characterize these 3D particle geometry, again, such as surface area, volume V, and shape beta, things like that. So after this, the researchers try to plot shape distribution, something like this. So x-axis about the shape angularity, and so similar to the particle size distribution on the left, right? So now we can better characterize the particle geometry, but there are still some limitations. First, the information is not synced. So for example, if I want to determine the particle shape of this particular size, I cannot, because this information is not synced to the plot on the right side. Likewise, if I want to determine the size of this particular shape, I cannot, because the particle shape distribution is not connected to the particle size distribution on the left. So we are looking at one set of particles, but presented the information separately, but those are not synced. So that is the one limitation. The second, there's no information still about the surface area and volume. We actually need to present this one, but we haven't. We can simply, put more plots on the right side. So like surface area distribution, the volume distribution, or surface area to volume ratio, A over B, the ratio distribution, something like that. But again, if we present those plots separately, those information will not be synced. So, well, definitely something's better than nothing, but well, that's not really quite useful. I would say can be more useful if we somehow sync those information, right? And also, I just like to mention A over B ratio is also known as specific surface area. That is known as a major factor that controls many physical phenomena such as drainage and the particle transport. So, how can he present all these four dimensions of 3D particle geometry in a more synced and comprehensive manner? Okay, how can he put all this information into a single space and better characterize the 3D particle geometry? So this is what I propose. So my idea is we may use log transformed A over V and B space. And then we can put everything together into a single space. So x-axis is a log of A over B, A over the surface area to volume ratio, and the vertical axis y is log of the volume. So whatever data points here on this space, we can get the surface area and the volume information. Then what about the particle size? Relatively simple, considering the equivalent particle size can be obtained from the volume B using this formula. So with that, we can add one more vertical axis, log of D, and then for whatever data points like this, we can get size, volume, and the surface area. Then my next question is, how can you get the shape on this space? So first, let us define the shape beta. And this can be defined as cubic area divided by scalar volume. The reason is the volume is three-dimensional measure and the surface area is two-dimensional measure. So we can formulate equation like this with constant lambda that depends on the particle geometry. Okay, so for different particle shape, the lambda will be different, right? So this equation can be reformulated in terms of A over V, and then we can see this beta term naturally comes out, right? And this beta increases with angularity. So as we can see, from sphere to cube and tetrahedron, beta value is increasing from 36 pi to 374. Okay, then how can you read this beta from this space? Okay, that is the question. So if this equation can be reformulated, the log transformed, and then we can present the equation this manner. Okay, so now you can see this is simple linear equation in log space, whereby this beta represents the intercept, and at A over B equals 1, that makes log 0, and then slope is minus 3. So for example, for this data point, if I want to evaluate the particle angularity, and then you can simply draw a line of slope of minus 3. And then the intercept at A over B equals 1 represents the shape angularity of this particular data points. Then my next question is, what if there are many particles? If you go outside and scoop of soil, you will have lots of particles, right? So then next question is, how can you determine the representative shape angularity? I will just use a symbol beta star for a group of particles. It's similar. So for a set of data points, we can determine the mean and then draw a line of with the slope of minus 3, and that represent the representative, the shape angular beta star. So that the beta star is indeed has the concept of the mean here. Okay, then you may see regression line of this data set is not equal to -3. So let me just use alpha to represent the slope. So then what does that mean? So that means actually the shape size relationship. So for example, this slope is more gentle compared to -3. So this is the first case. In this case, this alpha indicates the smaller particles are more angular. And to the opposite, I didn't present here, but it's something like this. Okay, it's steeper than -3. And then that indicates the larger particles are more angular than smaller particles. And if that the slope of the power regression line is -3, says there is no particular shape size relationship. For example, if all the particles that I have are spherical, there's no particular shape size relationship because whatever size you pick, those are spheres, right? So that means there is no particular dependency on the size. In broader sense, if all particles have same angularity, and then that also indicates there is no particular shape size relationship. If we plot the regression line, the slope will be -3, right? Okay, then how many particles do we need to scan? Just some number of particles that are enough to identify the regression line will be enough. The beauty of this approach is regression is very obvious. You may see the data points are not scattered, and that typically realize a very coherent linear relationship in the local space. That's because of the fractal nature. So the geometry is self-similar across scale, so mathematically it shows power law. So that is actually the straight line in local space. So this is an actual example from the mineral particles. So we scanned the 60 particles of limestone, the Florida limestone. And then you can see the data points are not much scattered and then showing very coherent linear relationship in this space. You can easily identify that power regression line. This is just another example of the crushed particle, and you can see this the data points are showing very coherent linear relationship. We scanned about 1,000 particles so far. We could identify all of the data sets are showing very coherent linear relationship. Okay. Right, this is my last question. So we are using particle size distribution in the engineering practice. This is common language used by the practitioners. So now the question is, how can you translate this particle size distribution in this new space? That's simple, actually. So by using this particle size, D0 and D100, as a guide, you can simply rotate and plug in this new space because we have information of size, as here you can see as a vertical axis. But that has to be after we identify the power regression line from the sampling. Okay, so we rotate and put it on top of this power regression line. So we have a D0, D100, and then we have a slope, so that will not be a problem. If you want to evaluate the shape angularity, and then you can do like this. So for example, for this 60, you can identify the point here, and then draw the line with a slope of -3. The intercept will represent the shape angularity of D60. Okay, something like this. Right, just to conclude, this is a new approach based on log transformed A over V and V space, so that comprehensively provide a complete picture of 3D particle geometry, the surface area, volume, size, and shape. And hopefully, this will help us to better understand complex macroscopic problem from the fundamental particle scale. So this research is funded by NSF. And for further details, you can go to this paper. For your information, I just provided QR code. You can simply scan and to get the access to the paper. Or you can just send me email if you have any further questions. All right, thank you very much.